In this video, we're going to learn how to find the multiplicity of a zero. So in the previous lesson, we saw that we got a same factor twice, and something happened with its behavior on the x-axis when that zero popped up more than once. So to learn a little bit of terminology, for this example, since the linear factor x plus 2 is repeated, that makes negative 2 a multiple zero, meaning it shows up multiple times. So since the linear factor x plus 2 appears twice, we can say that negative 2 is a zero of multiplicity 2. And that's what defines the multiplicity for us, is how many times that particular zero shows up in the in the polynomial function. So how do multiple zeros affect the graph? Well, if a number is a zero of multiplicity in the polynomial function p of x, then the behavior at the x-intercept a, the given number, will be linear if the multiplicity is 1, quadratic if the multiplicity is 2, cubic if the multiplicity is 3, and so on. Meaning the multiplicity kind of denotes the degree of that x-intercept. So a degree 2 makes it look like a quadratic, and a cubic, and a degree 3 makes it look like a cubic. So let's see what that looks like in an example just below. So reading this, I have a couple zeros. I have one at x equals negative 3, one at x equals 0 when I set x equal to 0, and one at x equals 2. The one where x is equal to negative 3 has a multiplicity of 1, so it should act linear whenever it crosses the x-axis. Typically, you don't have to put multiplicity of 1, but I'm putting it here right now so you can see how it changes the graph. For x equals 0 is the degree 2, so that's a multiplicity of 2. 0 comes up twice because the factor of x comes up twice. So 0 is a 0 of multiplicity 2, meaning it will look like a quadratic at 0. And for x equals 2, the x minus 2 factor shows up 3 times. So we said x equals 2 is a 0 of multiplicity 3, which makes it look like a cubic when it approaches the x-axis. So let's see how that affects the graph. First, I want to go over the end behavior. And just to understand this, you need to know at least its leading coefficient is, which again, you multiply all the leading terms of each factor, but raised to their powers. So we have x squared times x cubed, give me x to the 6 would be its leading coefficient. So its end behavior would be a positive x to an even power, so up and up. So in order to graph this, I'm going to draw each x-intercept, one at negative 3, the one at 0, and the one at 2. Now, the one at negative 3, initially, my graph is going up to the left. So it's up to the left, but when I'm approaching this x-intercept, it will be linear as I go through the points. Then I'll curve back up to go through the red point. Now the red point is quadratic as it hits the x-axis, so I'm not actually going to go through the x-axis. I'm going to bend towards the points like a parabola. See how you have that downwards parabola? So when this graph curves back up, it'll go back up, but it won't cross 0, but it kind of bend off of it like a quadratic would. And at 2, if it acts like a cubic, that means as I go through the points, it's going to kind of bend as such, like a cubic function would. So this graph would curl up, go through it like a cubic, like a little swerve through it, and then keep going. Ending my up and up end behavior, but you can see it's a line, it's a quadratic, and then it's a cubic as I go through that spot right there. So you'll see here, I'm going to leave my y-axis more or less empty as I go through these problems, so I don't have to find any y values. We'll just sketch, but we're going to see how these different multiplicities affect the behavior of these graphs. So first, let's find the zeros of each function, state the multiplicity of multiple zeros, meaning if it's multiplicity 1, you don't have to put this. And then, how does the graph behave at those particular zeros? So in order to find those zeros, we need to set our quadratic, or our polynomial, equal to 0. So x to the 5th minus 2x to the 4th minus x to the 3rd. And pardon me for saying quadratic. It is just 3 terms. Like, it's the first thing that came to mind. But this is a polynomial since the power is greater than 5. We'll set that equal to 0 and factor. So first I see that all the terms have something in common, which is x to the 3rd power minimally in each term. So I can factor out x to the 3rd, and I'll be left with x squared minus 2x minus 8. And now I'll be left with this quadratic factor on the inside, which I can continue to factor to give me x cubed times x plus 2 and x minus 4. So my zeros will be x is equal to negative 2 when I set x plus 2 equal to 0. But at multiplicity, it'll just be 1, so it's not a multiple 0. It will be x equals 0 because of the x, and that factor comes up 3 times, so we say 0 is a multiplicity. I'll just write out the word multiplicity of 3. And the last 0 is from x minus 4, which will just be 4. So whenever we have a multiplicity of 3, how does the graph behave at these zeros? For x equals negative 2, it'll be linear, because it's a multiplicity of 1. At x equals 0, it'll be like a cubic. At x equals 4, it'll be like a linear function. So see what that looks like if we were to sketch this. So we have a 0 at negative 2, 0, and 4. It goes through like a line. Before I start though, I don't know if I'm coming from the top or the bottom as I approach that negative 2. So to figure that out, I'm going to have to find its end behavior. Because its leading term is a positive odd degree term, its end behavior will be down to the left and up to the right, because it's positive, which means up to the right, and odd power, meaning they go in opposite directions. So when I graph this, I know I'm going to start low, so down to the left, but I'm going to go through like a line at negative 2. So straight through. And then now at 0, it should act like a cubic, which means I'm going to go up, and I'm kind of swerve through the points. That's what a cubic graph does. We graphed a few of them in a previous lesson. Then after I go through like a cubic, my graph ends by being a line through x equals 4. So I'll curve my graph back up and go straight through 4. So roughly it's what the graph looks like. Straight through negative 2, swerve through 0, straight through 4. Linear, cubic, linear. Now let's see what the next example looks like. I want to find its zeros first. So I'll set x cubed minus 4x squared plus 4x equal to 0. They all have an x in common, so I can factor that out first. And then this is a perfect square trinomial. So when it factors, it just becomes x minus 2 squared. The reason why I recognize that was a perfect square trinomial is the outer terms were perfect squares, and the middle term was twice of the 2 times x times negative 2. And the reason why that was negative is because that minus there. But this is a perfect square trinomial. Now I can set each of these factors equal to 0. So I'll get x equals 0 as 1, 0. But that's just 1, so I don't need to put multiplicity. And x equal 2 will be the other 0 of multiplicity 2, which means it'll act like a quadratic there. While the one at 0 will act like a linear function, since it is just multiplicity 1. So when I go to graph this, I'll graph both of those x-intercepts, so at 0 and at 2. And my end behavior for this graph would be down and up, because it's an odd power leading term, which means they should go in opposite directions. But since it's positive, it should go up to the right. So when I go to graph this, I start down. And again, it acts like a linear as I go through 0. So I'll start to go up. Go straight through, so it's like a line. Then I'll start to curve, but at 2 it has to act like a parabola, a quadratic. So when I go down, I'm going to kind of bend my graph, touch the point, and come back up. So it's similar to a parabola. So this is roughly what the graph would look like. And if we found points in between, we could be more accurate, but we're going to save a little bit of time there. So again, just to go back over, we had x minus 2 squared, which made that a multiple 0. And that came from the perfect squared trinomial in the step before. And that's what made that act like a quadratic at 2. But at 0, since it was just a 1 factor of x, it acted like a line as I went through 0. And that is how you find the multiplicity of a 0.